In this video, I'll try to demystify the Monte Carlo method with a simple example. This video is a sequel to the one outlining a quantitative risk analysis for a structure, such as a power line structure or ski lift tower in an avalanche path. In this example, let's consider a structure located in an avalanche path. Size D2, D3, and D4 avalanches from the path can hit the structure, as explained in the previous video. This video considers only the size D3 avalanches. They are expected to reach the structure about once every 10 years, so the annual probability of impact is 0.1. The structure is fixed in the middle of the path, so its probability of being exposed is 1. The average vulnerability is 0.1, meaning that, on average, the damage from D3 avalanches will be 10% of the total value. We can multiply the three average values to get an average annual risk of 0.01. This is useful, but it does not take into account the uncertainty in the probability of D3 avalanches or in the damage they cause. For examples, we are uncertain that the annual probability of the avalanches is actually 0.1. Also, some D3 avalanches may cause more than 10% damage, others may cause less. To get the distribution of risk from D3 avalanches, we need to estimate the distribution for the annual probability and for vulnerability. Let's start with vulnerability and consider its uncertainty. There are two types of uncertainty. First, not all D3 avalanches do exactly 10% damage. Some D3 avalanches have more punch and some have less. This natural variability is also called aleatoric uncertainty, which might look like this. Second, we are not certain of the minimum, average, or maximum. Neither are we certain of the shape of the distribution. This lack of knowledge is called knowledge source uncertainty or epistemic uncertainty. The wider distribution, including natural variability plus the epistemic uncertainty, is shown here. Potentially, knowledge source uncertainty can be reduced with more data or better models. Ideally, we would trigger many D3 avalanches above the structure and keep repairing it before the next avalanche. This would allow us to increase our knowledge of vulnerability and reduce the epistemic uncertainty. There is a key difference between the two types of uncertainty. We would like to reduce the epistemic uncertainty as much as practical. However, we want to include all the uncertainty due to natural variability, the aleatoric uncertainty. As in the risk table on the second slide, the distribution has an average of 0.1. I've chosen a minimum of 0 and a maximum of 0.25, which for the triangular distribution means the peak of the triangle is at 0.05. which is also called the most likely value or the mode of the distribution. The key to Monte Carlo simulation is to simulate the distribution of each of the input variables with thousands of values. Normally this is done with specialized Monte Carlo software packages, which have many advantages. Because I want to explain the basics behind Monte Carlo simulation, I'll use a spreadsheet. Here is the spreadsheet for vulnerability. The parameters of the triangular distribution are here. The simple function in this column generates random numbers between 0 and 1. There are 10,000 values in this column, but 5,000 would also have been adequate. In this column, there is a formula that generates values from the triangular distribution based on random numbers in the previous column. Note that each time I save the spreadsheet, the values change because the calculations are redone. To look at the distribution we have generated, let's use a histogram. The cells to generate the histogram are here. I'll skip the details, but there are 30 bars, and each bar shows the frequency of values for a slice of the random variable on the x-axis. Dividing the frequencies in this column by 10,000 gives us the relative frequencies in this column. Here is the histogram for vulnerability. The average is 0.1, which is of course the same as in the risk table on the second slide. The distribution has a minimum of 0, a peak at about 0.05, and a maximum of 0.25. Each time the calculations are done, the distribution changes, but only slightly. So now we have simulated the triangular distribution of the input variable vulnerability with 10,000 values. Now let's switch to the distribution for the annual probability of D3 avalanches. I chose a PERT distribution, also called a beta PERT, just to illustrate another common distribution used in Monte Carlo analysis. The average or mean is at 0.1, as shown in the table at the start of the video. I chose a minimum of 0 and a max of 0.5, which results in a peak at 0.03. There is another parameter called the kurtosis, which determines how quickly the distribution tapers on either side of the peak. I chose a kurtosis of 4, which corresponds to low confidence in the peak. I could have chosen higher values for moderate or high confidence in the peak, which would narrow the distribution as shown by the purple line. Here is the spreadsheet used to generate the PERT distribution, and here are the parameters of the distribution. In this column, there are 10,000 random values between 0 and 1. Since the formula for the PERT distribution is complicated, I've used a free add-in called OpenPERT, which generates values from the PERT distribution from the random values in the previous column. Here are the cells used to generate the histogram. This graph shows the histogram, that is, the distribution of uncertainty for the annual probability of D3 avalanches. Note that it has a minimum of 0, a peak at 0.03, an average at 0.1, and a maximum of 0.5. Of course, the distribution changes, but only slightly each time the calculations are repeated. Now we have 10,000 values for the annual probability and 10,000 values for the vulnerability. The exposure is fixed at 1. We multiply the first value in the spreadsheet column for the probability of avalanches times the first value in the column for vulnerability to get the first value in the column for risk. Do this for all 10,000 rows and we have the distribution for risk to the structure from the D3 avalanches. These cells generate the histogram. I've used many more bars than for the previous 2 histograms, but I'll only show the leftmost 30 bars. Here is the histogram for risk. The graph does not show all of the tail towards higher values of risk. Of course, the average is the same as in the risk table shown at the start of the video, 0.01. Let's put the distribution to use. First, we can visualize the uncertainty in the risk due to D3 avalanches hitting the structure. Only 60% of the uncertainty lies to the left of the average value of 0.01. So there is a 40% probability that the risk is greater than 0.01. 90% of the uncertainty lies to the left of 0.024. The Monte Carlo method allows us to choose the amount of uncertainty to consider when deciding whether the risk to the structure is acceptable or needs to be mitigated. Let's sum up. I used a spreadsheet to illustrate the workings behind a Monte Carlo simulation. However, specialized Monte Carlo software has many advantages. Trial versions and tutorials are available. The Monte Carlo method propagates uncertainty in our input variables through to the output variables. In this example, there was only one output variable, the risk to a structure from D3 avalanches in an avalanche path. Instead of making decisions based on average values of risk, the Monte Carlo method allows us to consider the uncertainty in our decisions. However, with the Monte Carlo method, we are often unsure that we have effectively represented all the uncertainty in our input variables. Of course, a major advantage of the Monte Carlo method is that people make better decisions when much of the uncertainty in the output variables can be considered. This video has only been a simple introduction to the Monte Carlo method, intended to take some of the mystery out of the method. My thanks to John Buffrey, Mike Conlon, and Chris Argue for their comments on an early version of this video.